Boom, and we're back in the same hoodie. It's actually the first few videos we've done it in hoodies. Kind of like it. Pretty comfortable, honestly. It's way better than the shirt and tie that I wear at school. Anyways, welcome back. In today's video, we're going over the power property of logarithms. It's like a tongue twister, all those alliterations. We're going to be going over a very quick proof as to why that property exists, as well as 3 problems to get you going in the right direction. All right. So if you like what we've been putting out so far, drop us a like and give us a comment. Let us know what you like, what you don't like. See if you guys need any homework help or something like that. We're always here to help you out. And yeah, let's do this. So what the power product? So what the power property? I really have to enunciate that because I keep saying power product. What the power property of logarithm states is that if you have some log base b with inside here you have some value raised to a variable, what you can actually do is just kick that exponent out and just write it right here as a coefficient. It's actually really, really useful. Arguably one of the most useful properties that we'll go over. And let's go over a little reason as to why, because it does kind of look weird, right? Because it's like, hey, if we're putting the power on top, right? And especially if you might get confused with PEMDAS or the order of operations. You might say, well, we're in the parentheses and now we're dealing with exponents. But you're telling me that what I would actually do is just be multiplying this on the outside? Why would the exponent go outside? And well, logarithms work a little bit differently, and here's actually why that is the way that it is. So first things first, let me just write a logarithm equal to a value. So let's just say that I have log base b of x, and let's say that is equal to m. Again, arbitrary, it does not matter what I set it to. So now that I have some logarithm with to some value equaling to some other value, our handy dandy loop-de-loop right there is going to mean that b to the power of m equals x. And I'm actually going to move this one up here and just so I can save a little bit of space. So b to the power of m equals x. So what I'm going to do now is I'm going to raise each of these to the power of k, because this is to the power of k. So let me write b to the power of m to the power of k is equal to x to the power of k. And if you're wondering how would you know to do that, it seems like you're kind of doing it out of thin air. You are. What you'll find a lot of times in math proofs is that you're basically manipulating things in such a way that you can somehow derive a property or a simplification. So when you see like, well, I don't see a k anywhere except for in this initial proof, but how would I know to raise it to that power? You actually don't really. Since this is the power property, it does make sense that we'd be raising it to a power. But if it seems just kind of weird and random, it is kind of weird and random. You're not the only one to be confused by that. So now that I have this written out, let me make sure that I can actually write this without exponents. I'm sorry, without parentheses. Of course, we're going to leave the exponents. So we'll have b to the power of mk is equal to x power of k. And now what I'm going to do is I'm going to take the logarithm of each side of this equation right here. So if I have the logarithm base b of some b to the mk is equal to log base b of xk. Cool. So there is a logarithm property, and again, this kind of goes back a little bit of the loop-de-loop thing, where if I have log base b and I have that same number right here, well, then this whole thing is going to be equal to 1, because b to the power of 1 equals b. Okay? So what ends up happening is that this over here is actually just going to be equal to mk, because again, I am taking the logarithm of some number with the same value for the base. So again, this to the power of 1 would equal this. So I can simplify that down to 1. So I have mk, my exponents left over. And now I'm going to have log, writing with my highlighter, or laser pointer technically, b to the xk. So let's not forget what we said m is. M is equal to log base b of x. So let's actually rewrite that. Let's write log base b of x. And I'm multiplying that by k, because again, this is m times k, so this is also m times k. And what is that equal to? Log base b of x to the power of k. So I actually have it right now. Let me kick out the log to the front. I'm sorry, the k to the front as a coefficient. Log base b to the x to the k. And there we go. That's it right there. So what I have just shown you is that through a couple of steps and a little bit of algebraic manipulation, I have just shown that what you can do is when you have that exponent in what you're taking the log of, you can actually take that exponent, move it down in front as the coefficient. So now that we know why this is the way that it is, let's take a look at just a couple of problems to make sure that we understand how to use the property effectively. So I have log base 2, 8 to the power of 3. I know that I can kick this 3 out. So let me write this as 3 log 2 of now 8. Okay, so now thinking of my loop-de-loop thing, what power do I need to raise 2 to get 8? Well, 2 to the power of 3 equals 8. So I know that 2 to the power of 3 equals 8. So 3 is what this is right over here. So that's going to give me 3 times log 2 to the power of 8, which I know is 3. Total final answer is 9. So let's take a look at one that's a little bit more difficult. Okay, so let's say I have log base 10 of 100 to the power of negative 2. So again, I'm going to take this negative 2, I'm going to kick it out as a coefficient. So I'll have negative 2 log 10 of 100. So again, same thing, that little loop-de-loop thing. I know there's no equal sign or variable over there, but still the idea being, what power do you raise 10 to get 100? What power do you raise 10 to get 100? Well, 10 squared is 100, so x is just going to equal 2. So I'm going to have negative 2 times log 10 of 100, 2. Negative 4. Now let's take a look at one that's a little bit more challenging. All right, so now I have an actual expression. I'm not just simplifying for the sake of simplifying. I'm actually trying to figure out what x equals given certain parameters. And what I'm given here is that the log base 5 of x cubed is equal to 6. So what value of x makes this statement true? Well, let's just go over our properties again. I know that this 3 can be kicked out in front. So I'm going to have 3 log 5 of x is equal to 6. Now you might be thinking, what do I do here? Well, remember, 3 is now just a coefficient. This is 3 times log base 5 of x. So I can just divide each side by 3. Once I have that, I'll have log base 5 of x is equal to 2. And now I have something that looks very similar to what I'm used to, where I can just use my little loop-de-loop thing. And I know that using this loop-de-loop, I know that 5 to the power of 2 equals x. What's 5 to the power of 2? 25. So I know that 25 is equal to x. So what this means is that log base 5 of 25 cubed is equal to 6. And let's actually further verify this. That would mean that log base 5 of what, 25 cubed? 25 cubed is, pause the video, I don't know it off the top of my head actually. It's 15,625 is equal to 6. So the question is, does 5 to the power of 6 equal 15,625? Well, I'm actually just going to go over my calculator here, and I'm going to go 5 times 5 times 5 times 5 times 5 times 5. 15,625. 15,625 equals 15,625. We are all set. Boom, there it is. So yeah, hopefully this shed a little bit of light onto why you can just take an exponent and kick it out in front as a coefficient. There is a method to the madness, I promise, and hopefully some of these example problems helped clarify how to use it effectively and properly. Okay, so if you appreciated that, go ahead and like, comment, and subscribe. It'll really help us out on the channel. We're going to be producing a lot more videos on not only these kind of mathematic tutorials with some examples, but also some tips to help you guys study and maybe some other things that might just help you out in the classroom and get through high school and college a little bit easier. All right, so hope you all are doing well. For me, I'm on spring break officially. I hope you guys are, whenever, wherever you're watching, everything's all good. All right, so take it easy. Have a good one. See you later.